Okay, we talked about these last year. This is actually identical to what we did last year, except it was Unit 6. We called it Unit 6. Sorry, yeah, Unit 6, grade 11. Rational functions. When you see the word rational, you should be thinking fraction. Okay? Because that's exactly what a rational function is. It is a function that can be expressed as a fraction. Some polynomial over another polynomial. And this polynomial can never work out to 0 because we can't divide by 0. Okay? Let's look at the most basic rational function. Remember, when we did quadratic functions last year, we looked at the most basic one, x squared. This year, when we did radical functions, we looked at the most basic one, root x. Okay? The most basic rational function is 1 over x. To show you what it looks like on a graph, we're going to start with a table of values. So these are pretty straightforward. If x is -2, this is going to be -1/2. If x is -1, 1 divided -1 is -1. If x is -1/2, 1 divided -1/2 is the same as 1 times -2 over 1, which is -2. If x is 0, what's 1 divided 0? Undefined. There is no value. So there is no point on this graph when x is 0. If x is 1/2, 1 divided by 1/2 is the same as 1 times 2 over 1, which is 2. If x is 1, 1 divided by 1 is 1. If x is 2, 1 divided by 1/2, or 1 divided by 2 is 1/2. If we plot these points, okay, so we get -2, whoops, one way. -2, -1/2, -1, -1, -1/2, -2. So those 3 points are down in that quadrant, quadrant 3. There is no point on the line when x is 0. And then we skip over, and now we're up here, 1/2, comma 2, 1, 1, and 2, 1/2. Okay? So we actually end up with 2 sections of the graph. There's a couple of areas on this graph where, like, the graph does not cross. It gets close to, but it doesn't touch or it doesn't cross. We have talked about those, what those are. Okay, when a graph gets really, really close to some line, but doesn't cross it, that's an asymptote. Okay, and we've done asymptotes already this year. We did it with exponential functions. We did it with logarithmic functions. Okay, remember, with exponential functions, there was a horizontal asymptote. With logarithmic functions, there's a vertical asymptote. With rational functions, there can be both. Okay, most of the time, most of the ones we'll look at, there's both. So there's no point on this graph where x is 0. So we sort of have like a little curve here, we have like a little curve here. Okay, but there's no point on the graph where x is 0. So it kind of jumps over the line x equals 0, which is the y-axis. And that is the vertical asymptote. Okay. So we draw. What's that? This line, last year I used it to define what an asymptote is. You guys know what an asymptote is because we've been dealing with them for a while. So where do we find the vertical asymptote when we look at the function? We find it at the non-permissible values of the rational function. So whatever x can't be, the non-permissible values, whatever makes the denominator 0, those will be the vertical asymptotes. There is also no point on this graph where the y-coordinate is 0. Because how can you do that? Like if you make y equal to 0, 1 divided by what number is equal to 0? There is no such number. Okay? So we have another bridge. This time it's a horizontal bridge. And we call it the horizontal asymptote. Okay. We've got most of the graph, but the question is, like, what's happening over here? What's happening in between here? And what's happening over here? Okay? Well, if we look at the ends, like, let's look at this end. If x is 3, then I get 1/3, right? If x is 10, then I get 1/10. Keeps getting smaller and smaller and smaller, but never hits 0. So I draw a line like that. It goes along y equals 0, but never hits it. Same thing in the negatives. If we did -4, I get -1/4, close to 0. If we did -10, I get -10, even closer to 0. So the graphs continue like so. What's happening around here? Well, if we look at this, the closer I get to x equals 0. So like if x equals 1/2, then y is 2, right? If x is 1/10, y is 10. If x is 1/20, y is 20. So as I get smaller and smaller and smaller on the x, I get bigger and bigger and bigger on the y's. So it goes like that. And the same reasoning applies to this section down here. So my final graph looks like this. It's basically made up of 2 curves that continue along the horizontal and vertical asymptotes. Okay? What I just said can be summarized here. Okay? Behavior near non-permissible value or vertical asymptote. As we approach y from the right, the y-axis, okay? Sorry, as x approaches 0 from the right, the y gets bigger and bigger. As we approach it from the left, it's getting smaller and smaller. On the ends, as we continued off to negative infinity and positive infinity, y kept getting closer and closer to 0. Okay, some properties. The x-intercept. There's 2 ways you can do it. You can look at the graph and see where the x-intercept is, or you can use algebra. Okay? You look at the graph, what's the x-intercept? Where does it hit the x-axis? No, on this graph, y equals 1 over x. What is the x-intercept? There is none.
because it never touches the x-axis. It also never touches the y. And we could have done that using algebra. We could have said y equals 1 over x, or 1 over 0, y-intercept undefined, which means it doesn't exist. Or I make x equals 0 and I need to figure y equals 0, and I need to figure out what x is. There's no value for x that I can divide 1 by x and get 0, so x-intercept also undefined.
Okay, for the domain and range, this is where we use the not equal signs because it's easier than interval notation. Okay, interval notation, you can use it, but it's pretty complicated because if you look at the domain of this one, it goes to negative infinity, it goes to positive infinity, but it doesn't include 0, does it? So it's every x value is the domain except 0. That's hard to write in interval.
In the other notation, it's easier. You just simply write x not equal to 0.
That means x can be anything, but it can't be 0. Similarly, for the range, it goes down forever, it goes up forever, but y is never 0.
So y cannot equal 0. We can transform
rational functions, just like we did with a lot of other functions throughout the year. Okay?
Notice this is the form a rational function takes in transformation. A, what does that represent? Vertical stretch. Also, vertical flip if negative. H represents horizontal shift. That means we're going to shift all the points on the graph and the asymptotes left or right, left or right. K represents a vertical shift. That means we're going to take everything on the graph, asymptotes and all, and move it up or down. Okay? Notice there's no horizontal stretch here. Okay? Because you can turn any horizontal stretch into a vertical stretch on a rational function. Like, for example, this. Okay? One would think, okay, this is B, right? But can't I do this? Got rid of the horizontal stretch. It just turns into a vertical stretch. That's why we never use B. When a rational function shifts, its asymptotes shift. Okay? One of them will shift, the other will not. When we have a horizontal shift, the vertical asymptote moves. Because, right, remember the vertical's like this, so it will move. So the vertical asymptote shifts. when we shift up or down, the horizontal asymptote shifts up or down. So a vertical shift, kind of have to think opposite. It means horizontal asymptote shifts. Okay, all I want to do to finish up, we've got about 13 minutes, is I want to sketch these two. Okay. How do you sketch these things? Well, get the asymptotes, get points on either side of the vertical asymptotes, and then you'll have your graph. Okay? So this is what I mean. First of all, remember, in 1 over x, the asymptotes are both 0, right? The vertical asymptote is 0, the horizontal asymptote is 0. But this is shifting the vertical, right? Horizontal shift -2, that means that the vertical asymptote goes from 0 to -2. So it's going to be here. Normally, our horizontal asymptote is y equals 0, but there's a vertical shift. So there's a vertical shift of -3, which means the horizontal asymptote moves down 3 as well. So it becomes y equals -3. So we're down here. We know what the graph looks like. It's going to be 2 curves, right? The question is, where are the 2 curves? Here, 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 here. Not sure. I need some points. Where do I find the points? Go to the vertical asymptote. Pick the x value directly to the left and the x value directly to the right, and find the points. So x is -3, x is -1. Those are the other points I want to know. So I want to know when x is -3, what's y? When x is -1, what's y? Well, I plug -3 in here. So I get 1 over -3 plus 2 minus 3. Oh, this gives me -1. 1 divided -1 is -1. Minus 3 is -4. That means one of my points is -3, -4. The second one, when x is -1, 1 divided -1 plus 2 minus 3. That gives me 1 on the bottom. 1 divided 1 is 1, subtract 3 is -2. So another point on the other side of the vertical asymptote is there. Plot them. So -3, -4 is there. -1, -2 is there. And we know that they go like this, right? So finish the graph. You're done. I'm not going to worry about the intercepts or domain just yet. Let's move on and graph this one. And we do it the same way. What does this mean? Okay, which means which asymptote's going to move 3? Vertical's going to move 3 to the right. So it's going to become x equals 3. This means what?
Vertical shift.
Vertical shift up 4, which means which asymptote is moving? Horizontal moves up 4. So y equals 4. Now, if we see the shapes of these graphs that we've done so far, notice we get the curve in the upper right and the lower left where the asymptotes cross, right? So one would think that we would get them here and here, but there's a negative in that numerator, isn't there? Wouldn't that mean that they flip? So chances are they're going to be here and here. How do we know for sure? Pick a value on either side of the vertical asymptote. What values of x am I going to pick? 2 and 4. Okay. So if x is 2, I get -1 over 2 minus 3 plus 4. Well, 2 minus 3 is -1. -1 divided -1 is +1. Plus 4 is 5. So 2, 5. When I plug 4 in, I get -1 over 4 minus 3 plus 4. That gives me -1 divided 1, which is -1 plus 4 is 3. Okay. Plot those, and you'll see that they do, in fact, this time appear here and here. So I get 2, 5, 4, 3, and it makes sense. Okay. I'm not going to worry so much about the properties. The properties are in the notes. Okay. What I'm concerned about is that you know how to graph these and you understand about the asymptotes. Okay. Now, the rest of this lesson deals with 3 certain types of rational functions when we have x squareds involved. And we talked about those last year. Okay. You can have a look at them, not a huge deal. What's more important is that I want to do 11.2 on Tuesday, okay? Because 11.2 is a really good lesson on how to just take any rational function and graph it, okay? And sometimes when we have rational functions, we don't get asymptotes, and I'm not sure if you remember this from last year, we get holes in the graph, okay? And we'll talk about those as well. Then you should be fully prepared for Wednesday and June 9th. Well, I mean, obviously you're going to have to do some preparation. You get my idea.